Hello everyone, hope you all are doing fine. Welcome to Shaurav's classes. So today's topic for the video is tomato problem solving session, objective part. Those who are new to this session, I want to tell you that tomato is the abbreviated form of Test of Mathematics and 10 plus 2 level, which is a book published by Indian Statistical Institute, including the past year questions of Indian Statistical Institute and as well as some additional questions which the professors think must be given to qualify the exam. So Indian Statistical Institute is, those who have heard the name for the first time or you have encountered the name for the first time, the Indian Statistical Institute is one of the most premier institutes in the fields of study like maths, science, statistics, computer science, physics, etc. So getting into that, you need to get into an entrance exam, the problems of which are listed in the book called Tomato, Test of Mathematics at 10 plus 2 level. So this book is published by ISI themselves. You can get it on Amazon and Flipkart. For any doubts on Tomato, you can always refer to Shaurav sir's classes, study materials, and exquisite range of study materials it has, which deals with problem solving for ISI and CMI as well as CMI, the two premier institutes. So if you get an ambition to get into ISI or CMI, so please don't forget to contact two things. Number one is Tomato and number two is Shaurav sir's classes. So today we are in the objective portion. The entrance test at ISI includes two parts. The paper is divided into two parts, the objective part and the subjective part. And we will be solving problems from the subjective part today, and here we are with our first problem written on the board. So the first problem says that if xn plus 1 equals xn by 1 plus xn for all n greater than equals to 1 and x1 greater than minus 1, it is given x1 greater than minus 1, then limit n tends to infinity xn is minus 1, 0, 1 or does not exist. So I give you some time to solve this question and just try it on your own, because trying on your own is a very important thing. Okay, so the stipulated time meant for this question is over and I'll start solving the question now. So before solving the question, I'll teach you a very important concept. So when limit of a sequence exists, the sequence is said to be convergent sequence. Now this is a sequence which says that this is a sequence that is given. And how is the sequence defined? The sequence is said to be defined recursively. So this is an example of a recursive sequence. Now recursive sequences can be solved and written in explicit or implicit form. But here you can see that this sequence has this term based on the previous term. So if in any sequence one term is based on a previous term, the sequence is known as recursive sequence. Now such sequences can be solved such that it might be made independent of this term and can be written implicitly. But these types of recurrence, there are many recurrence which need not be solved, which cannot be solved. In fact, mathematicians are still working on methods to solve these recurrences. But in this recurrence, that is in the question, given in the question, we basically don't need to solve this question, recurrence. Without solving, we can just get into the solution with a very simple trick. So let's see what is. So first of all, let me state a theorem. The theorem says that any bounded monotonic sequence is convergent. What does convergent mean? As I have told, convergent means limit exists. So it says that any monotonically bounded sequence, for any monotonically bounded sequence, the limit exists. So any monotonically bounded sequence limit exists. So this is a very important result that I recommend everyone of you to remember and apply this. So if I have to prove that the limit of this sequence exists, then what do I have to do? I have to prove it both monotonic and bounded. So let me try proving that this sequence is monotonic. So we see that if xn is positive real number, or if xn is a real number, then xn plus 1 is always greater than xn. For xn belongs to real numbers, for any real number. And since here it is given that xn is not equals to minus 1, I can divide both sides by xn. What can I get? So this is what I get. So xn by 1 plus xn is less than 1. Okay. So what I do is, let's say 1 plus xn, I mean to say which is greater than 1. So this is a very true relation. So 1 by 1 plus xn is less than 1. That we can prove. So if you forget this step, so I recommend you to forget the second step and see that since I just use the inequality, since xn is greater than minus 1 as was given in the question, so xn plus 1 is greater than 1, isn't it? So 1 plus xn is greater than 1 and 1 by 1 plus xn is less than 1. Now we multiply both of these sides by xn. And we get this. Now what is this? According to the question, this is xn plus 1. And so we have found that xn plus 1 is strictly less than xn, which implies to say xn is monotonic. Therefore, we have proved this sequence is monotonic. Isn't it? So we have proved that the sequence is monotonic. And we are now left to prove that the sequence is bounded. Now for the sequence is bounded, we will get back to this inequality. From the first inequality, I can say that xn by 1 plus xn is less than 1. Which means xn plus 1 is less than 1 for all n belongs to natural numbers. Which means xn is bounded. So I hope that I am not clear. So let me explain the proof again. So first we have successfully proved that xn plus 1 by is less than xn, which proves, so how do I prove? I assume xn by 1 plus 1 by 1 plus xn is less than 1. So 1 plus xn is greater than 1 always. This is because xn is positive. Now 1 by 1 plus xn is less than 1. Xn by 1 plus xn is less than xn and xn plus 1 is less than xn, and therefore we have proved that xn is monotonic. And of course xn plus 1 is always less than 1. So xn is monotonic, or say we can say that xn is monotonically decreasing. And we have assumed and we have saw that xn by 1 plus xn is less than 1 from this inequality. And from there we have gained that xn plus 1 is less than 1. Therefore xn is bounded above. But bounded above doesn't necessarily mean bounded. For a sequence to be bounded, it must be both bounded above and below. And it is not very difficult to observe that xn greater than 0 for all n. And this can be easily proved by principle of mathematical induction. So xn is monotonically decreasing and xn is bounded, therefore limit exists. So let me repeat, since xn is monotonically increasing and xn is bounded, therefore limit exists. Now we need to find that limit. So why did I first prove that I have to prove that the limit exists? Because of that fourth option. The fourth option says that does not exist. So we have successfully proved that limit exists. Now after having proved the existence of the limit, now we can easily just substitute L for limits and we can just get out the value of L. So L plus L square equals to L. So this, since L not equals to minus 1, I must write it. And so L square equals to 0, which implies L equals to 0. So the limit exists and is equal to 0, and according to Tomato, the answer is option B. So we have seen that how important the theorem was, the result was, that any bounded sequence which is monotonic and bounded, so any sequence which is monotonic and bounded converges, which means tends to certain limit. So without wasting further time, let's get to the second problem of today. So it says that the value of double summation ij, where I greater than equals to 1, j less than equals to 10, is option A 1320, option B 2640, option C 2045, and option D is none. So I'll give you some stipulated amount of time to solve this question. Remember that in the ISI entrance exam, you need to face 30 objective questions within 2 hours. That is, if you divide 2 hours is 120 minutes, so 120 minutes by 30, you have 4 minutes on one question. So I recommend you to solve this question before 4 minutes, and I'll get into the solution at the end of 2 minutes so that you have a regular practice and you can just tally with the solution of yours. Okay, so the stipulated time meant for this question is over. So if you could solve it, then it's very good, and if you couldn't solve it, don't be disheartened, because you will learn a fabulous concept right now so that you will be able to deal with double summations like this. Now, first of all, let me make you understand that what does this expression actually mean. So let's try it for lower expressions first. Less than equals to I, less comma j, less than equals to 3. So let's make it to 3 terms. So what do I get? 1 into 1 plus 1 into 2 plus 1 into 3 plus 2 into 1 plus 2 into 2 plus 2 into 3 plus 3 into 1 plus 3 into 2 plus 3 into 3. So this is the expression that is means all possible products of the combinations between 1 and 3 are to be added. So this is basically the notion for double summation. And what does it result to? It results to 1 plus 2 plus 3 plus 2 plus 4 plus 6 plus 3 plus 6 plus 9, and it might amount to something value. But the value is not what we are interested in. We are interested in observing a pattern. Notice that if I take this same expression can be written from here as if I take 1 common, I get 1 plus 2 plus 3. If I take 2 common, I again get 1 plus 2 plus 3. And if I take 3 common, I again get 1 plus 2 plus 3. Which is nothing but 1 plus 2 plus 3 into 1 plus 2 plus 3. Now tell me which sum is much more easier to compute. This sum or this sum? Of course, this expression is much more easier to conclude. This is because this expression from the addition, this tedious long addition, I have been able to decrease successfully into 2-term multiplication. Isn't it amazing? And now I will apply this same concept and same technique to solve this problem. Just follow the steps. So in our original problem, it was I to j less than equals to 10. And following the pattern over, I can write it as summation of the same thing. I am just not writing this. So it's I into summation of j from 1 to 10, isn't it? Which is nothing but summation I equals 1 to 10 I into 55. As you know that the summation of 1 to 10 is 55, and I can take 55 common outside into summation I equals to 1 to 10 I, which is 55 into 55, and hence it is 3025. And according to Tomato, the answer is option C. So we have observed an important idea or an important technique of this question. So the technique was that we have observed the pattern. So pattern recognition sometimes forms a very important technique in problem solving, and you must always look for patterns and small results when you are solving a problem, when you are attempting to solve a problem on your own. So just like this pattern helped me, and similarly you might get double sum, triple sum, 4 times sums, and you will all be able to solve it with this thing. So without further ado, let me get back to the next problem. So if in a sequence an of natural numbers, then this is the third problem for today. In a sequence of natural numbers, an plus 1 is equals to an into an plus 1, where a1 is defined to be 2. Then an, what does it does? Converge, diverge, has bounded oscillation, has unbounded oscillation. So similarly, I want to give you a stipulated time to solve this problem on your own. Okay, so the time limit meant for this question is over, and if you couldn't, and again the instruction goes the same, so if you couldn't solve the question, you can just tally with the answer, and if you solve, then just see this. So the question says that if an is a sequence of natural numbers and a1 is defined to be 2, so I'll explain you a general strategy of solving these questions. So these type of questions do not require any additional knowledge of sequence, series, convergence, divergence, etc. So I'll give you a very logical law which you can just utilize to solve questions like this. And the core concept that to be developed is the Abel-Pringsheim law. The Abel-Pringsheim theorem. So the Abel-Pringsheim theorem says that if an plus 1 as an plus 1 is greater than an and an diverges, implies an plus 1 diverges. Okay, so what does the Abel-Pringsheim theorem says? It says that if an plus 1 greater than an and an diverges, then an plus 1 automatically diverges. And so I see that you have got this theorem, and now we will apply this theorem to solve this problem in a single step. So what does the problem represent? So the problem represents sequence of natural numbers an plus 1, an into an plus 1, where a1 is 2. So then an. Now suppose an plus 1 is the sequence of natural numbers. Now we know that there are infinitely many natural numbers, and therefore any sequence, any infinite sequence of natural numbers must always diverge. Therefore an diverges, and since we have an plus 1 is equal to a into an plus 1, which is greater than an, therefore by the result that was tested, an diverges. So which effectively means an diverges. So we see that how shortly we could solve the problem in a few lines by using that result. So I recommend you to remember that result and apply it to larger problems so that you can solve problems very easily using that theorem. So last but not the least, so this is the end question of this video session. So it says that there is a sequence of number. So the question, last question, f1 equals to 1, which is equals to f2, and fn equals fn minus 1 plus fn minus 2. Fn minus 2, so if fn is the remainder, then f2000 equals what? Small f. So we are back to the last question. So it says that if f1 equals to 1, f2 equals to 2, and fn equals fn minus 1 plus fn minus 2, then if fn is the remainder when capital Fn is divided by 5, then f2000 equals 0, 1, 2, 3. So it just needs the remainder of f2000 according to the sequence is divisible by 5. So you need to find the remainder. So I give you some time. So the stipulated time meant for this question is over, and now I want to solve this question so that you can tally with the solution and also get an important concept. So before this, the relevant concept that is required to solve this problem is the Fibonacci numbers. So Fibonacci numbers are the numbers that was defined in the recurrence in the question. So f1 equals to 1, f1 equals to 0, f2 equals 1, and fn, or in the question it was given as f1 equals to 1, a equals to fn minus 1 plus fn minus 2. Okay, so this basically is known as Fibonacci sequence. So there are many results. Concerning the Fibonacci sequence, but I am not going into details into all of them now. So Fibonacci sequence was defined first by the famous mathematician Fibonacci, and so I'll only discuss about the particular result of Fibonacci sequence right now. It says that remainders, so concept is remainders after dividing fn by k is periodic. So this is the core concept of the core results, or the central thing around which this problem revolves. It says that remainders after dividing fn by k is periodic, which means that if you continuously divide all the terms of this sequence by k, eventually you will get the same term after some definite amount of space. The space means after some definite amount of terms. So using this concept, so I can just give you an example that 1, so what is the first one? 1. Second one is 2. Third one is 2. Fourth one is 2 plus 1 is 3. The fifth one is 5. The sixth one is 8. The seventh one is 13. So let me just put comma so that you can separate it. The eighth one is 21. 34 and so on. Now what are the remainders mod 5? You can see that the remainders are 1, 1, 2, 3, 0. Again you can see it's 3. So 13 is 3 again. 21 is 1 again. And then 34 is 4. So this is how the Fibonacci sequence works. And after 4, the last is 0. And so this is how it goes on. Which means that every fifth term you can see is divisible by 5. So 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, 0. So as I have stated the result that the remainders obtained after Fibonacci sequence will be periodic, and therefore this 0 here will appear after a period of 5 because of that concept I have developed within you. And since f of 2000 is divisible by 5, therefore 2000 is 0. Problem solved. So the answer according to the Tomato book as I am seeing in front of me present is option A. So I think I am not very clear at the first time, so that it revolves the main the main idea of this problem revolves around the fact that remainders after dividing fn by k, that can be any k except 1 and 0, is periodic. So I have obtained the remainders, and since by using that concept I could see that after every fifth term 0 is appearing. So f 2000 must be 0, and therefore it solves the problem. So in this session we have learned about very important core concepts. We have developed much more accounts, and we have got much more ideas in depth. So I recommend you to solve these ideas and get and approach more problems from Tomato. Remember, until and unless you do problems by yourselves, these concepts in this video will remain as it is. They won't be able to help you. So I recommend you to solve more and more problems after seeing this video using these concepts so that you can be in a better position. For more info, you can get the study materials of Saurav Sir's classes and join Saurav Sir's Institution for ISI and CMI. These packages of study materials have immense use in clearing the ISI and the CMI entrance exams. They have a list of these techniques, a bunch of many other techniques than I have told here, which can be utilized to clear your exams. So all the best. Hope you all will be well till the next time we meet, and thank you.